All right, so in this brief little lecture, we're going to introduce our final type of reaction, and that's going to be these oxidation reduction reactions, which you're probably pretty familiar with. Um, Anything from the rusting of pipes to the explosion of the Hindenburg, and any combustion reaction is actually this type of reaction, this oxidation reduction reaction. And so, what we're going to try to get out by the end of this mini lecture, but it's really the end of chapter 8, is we're going to introduce this idea of oxidation and reduction, and then we're going to learn how to assign a numerical value to each atom to decide if it has changed in its state, to say if it has been oxidized or reduced. And so by the end, you're going to be able to determine for a given reaction what species is oxidized and which is reduced. And then you're going to do that by learning how to assign oxidation states to all atoms in a reaction. But before we get to that, let's look at a couple examples of these types of reactions. So we have combustion, like this explosion of the Hindenburg. We have also some very exciting reactions with metals and water, which I showed you when we talked about periodic trends. So if you add any of your alkali metals to water, what it'll do is it'll produce, in a very violent reaction, some H2 gas, which is then ignited and is burned. But there's also some more benign and like calm reactions. Like there's combination reactions that we can utilize to make something like NaCl, which we talked about how sodium and chlorine are very reactive elements, but when you bring them together, they give us salt. And then we have what is, for all intents and purposes, the opposite of a combustion reaction, and that's this decomposition reaction here, where we can turn water into something like H2 gas and O2 gas. And this has applications in fuel cells. And what's key to all of these is that there's a change in number of electrons for the elements. So electrons are being exchanged in these types of reactions. And so let's go through and talk about each one of these, these terms we're using for oxidation reduction. So these reactions are, as I mentioned before, reactions in which electrons are transferred. And they're going to be transferred from one species to another. And so we have terms for where electrons are coming from and where they're going. And so the term for where electrons come from is going to be oxidation. This is simply going to be the loss of electrons. And an example of this would be the loss of electrons by sodium metal as it turns into its ionized Na plus state. And we saw this before, this ion formation for sodium. We talked about the energy associated with this, and that was the ionization energy. And we're going to see for us that often this ionization and this loss of electrons tends to happen with metals. So metals lose electrons. On the flip side, we have reduction. And if oxidation is the loss, reduction is going to be the gain of electrons. An example is fluorine, picking up an electron and becoming the fluoride ion. And we talked about how well something attracts electrons to itself in electronegativity. And then the energy released when atoms accept electrons, we said, was the electron affinity. We said that there's a certain energy released when this occurs. And we're going to see that this act of reduction is largely going to happen by nonmetals. So nonmetals gain electrons. And if we want to remember what oxidation is and what reduction is, we can use one of two mnemonics. We have oil rig, which says that oxidation is loss, reduction is gain, and we can go up to each of our things before, looking at oil rig right here in yellow, where oxidation of sodium was the loss, and it's the loss of electrons. And the RIG of rig is reduction is gain of electrons. That's the one I personally prefer. You can also use Leo the Lion Says Gur, which says that losing electrons is oxidation, gaining electrons is reduction. And that is simply just a personal preference of whichever makes the most sense to you. But you can see that if one step of oxidation reduction is the loss of electrons, one step is gaining them, as you might imagine, what's going to happen is that those electrons are simply going to be exchanged. So we're going to see that electrons lost by one species must be gained by another. They're not just going to, float out into the ether. They're going to be captured as they're lost. And so we said that the loss of electrons is oxidation. We said that the gain of electrons is reduction. And we're going to take part of each one of these words to describe the types of reactions that have electron transfer. Redox, the RED from reduction, the OX from oxidation. And so there's two more terms I want to introduce to you. And one of those is the reducing agent. So the species that undergoes oxidation is the reducing agent. So if we look at our sodium metal that then goes to make sodium plus, and I'll do the electron in black. The sodium itself right here, we would call this the reducing agent. It is the thing by which reduction can occur. It is the thing giving up electrons in order for something to be reduced. And then we have, on the flip side, that which is undergoing reduction is known as the oxidizing agent. So when chlorine goes ahead and accepts that electron, so this electron right here comes down over here, when we do that and we make the Cl minus ion, the thing that allows oxidation of something to occur is chlorine. It is that which is accepting the electron, allowing sodium to give it up. And so it's kind of like a cyclical process where one thing allows another thing to occur. And so we said that this gives E minus to reduce something. And then we said our oxidizing agent accepts E minus to oxidize something. And this terminology, just for your information, largely comes from the fact that oxygen is often the reducing agent, meaning that it often is reduced. And then a reduction in charge, the reason we use reduced is that a reduction in charge equals reduced. So oxidation, because oxygen's the thing that has it happen, or the thing that does it. Reduction, because we're seeing a lowering of charge there. And you can think of these redox reactions as just a paired reaction, just like acid-base, because we said that acid-base chemistry usually happens in tandem as well. And so far we've talked about metals giving up electrons to nonmetals, but this is not the only way that redox can occur. You can also have redox happen with nonmetals. And one case is this one right here, where H2 gas plus chlorine goes on to make HCl. And for each of these species, when they're just by themselves, I'm showing you those electron density maps where blue means that there's low electron density and orange means that there's high electron density. These are two nonpolar molecules. But when you put them together, when you make two equivalents of HCl, we know that this right here, this HCl, and I'll put it in blue as well, this in and of itself is polar. We can draw the bond dipole. We write our H, we write our Cl right here, and our bond dipole points this way. And in essence, what's happening here is a redox process. So hydrogen used to have electron density, but because of the polar bond, it's losing that electron. We said when we talked about polarity, it's like hydrogen has a partial positive charge because it's partially lost its electron. So if we say that hydrogen loses electron density or has lost electron density, we can think of that loosely like, by our strict definition, the loss of electrons is oxidation. So hydrogen has been oxidized. It's experienced oxidation. And then on the flip side, if we look at that chlorine, it has that partial negative charge because chlorine has gained electron density. And in this case, it's not that we have a full gain or loss of that electron, it's that partial loss. We said that polar bonds are a partial movement of that electron, that unequal sharing. And so because chlorine has gained that electron density, we can say that it has been reduced. And so if we're going to talk about, hydrogen being oxidized, chlorine being reduced, and we don't want to sit here and analyze each polar bond, what we want to do is we want to use a method that allows us to track the movement of electrons between nonmetals. And so what we're going to do is we're going to do that using something called oxidation states or oxidation numbers. So let's talk about that. So oxidation state / number, we can use each of these interchangeably, is a bookkeeping method for tracking electrons. And so in this method, like formal charge, we're introducing to you another concept. But in this method, shared electrons are going to be assigned to the most electronegative atom. So I need to put the T here. Electronegative atom. Okay? And then as we've assigned these electrons, we're going to see that the atoms adopt an oxidation number, which is the pseudo charge an atom will have. An atom has in a compound according to the unequal electron sharing. So according to unequal electron sharing. And so this is just a way that we track the electrons. It's not an actual charge, but we've gone from the polar perspective where we said there's this partial movement of electrons to now we're just going to say like the electron has fully moved for the purposes of talking about electron movement. And so we already drew HCl. We'll draw it one more time here. Here's H, here's Cl, and we have, our lone pair sitting around it like that. And so if we're going to assign the oxidation state, we said we're going to take all shared electrons and assign them to the most electronegative atom. And we know the electronegativities here are going to be 2.1 for hydrogen, 3.0 for Cl. And so this set of electrons right here is going to be owned by the chlorine. So we're going to say that chlorine has 8 electrons, and that leaves hydrogen having 0, because it doesn't have any lone pairs, and it doesn't get to keep those electrons that are in the bond. And so for the chlorine, just for the benefit of clarity, it has 6 electrons from lone pairs, and then 2 from the bond. Okay? And so we know that Cl, as a halogen, typically has 7 valence electrons. So you can think of this like when we did the Lewis model in formal charge, we said, how many valence electrons does it typically have? And then we're going to compare that to how many electrons it owns now. So it typically has 7 valence electrons. And right now it has 8. And it now has 8. So we'll do 7 minus 8. And we'll say that it has an oxidation state of -1. -1 oxidation state. And on the next slide, I'll point out that when we do oxidation states, we put the sign in front. When we do actual charge, we put the sign on the other side. And so on the flip side, we have our hydrogen, which typically has 1 valence electron. Right now, it only has 0, so now has 0. So we'll do 1 minus 0 equals a +1 oxidation state. And so, like I said, we're not actually breaking this bond. We're just assigning where the electrons are. And if you want to go a little bit more in depth, you can imagine that, chlorine gaining this last electron to give it 8 valence is the equivalent of it having, 18 total electrons. And you take the number of protons it has of 17. So you're just looking at the charge balance. So 17 protons, 18 electrons gives you that -1 oxidation state. And so we have a couple rules that we use in order to assign oxidation states. So once again, we don't have to look at each polar bond, look at which way the dipole goes, and then compare electronegativities. And so those rules are as such, and they're hierarchical, where we follow early rules before later rules. But we'll say that atoms in their elemental state get an oxidation state of 0. So if you have H2 gas, O2 gas, N2 gas, any of those diatomics, like F2 gas as well as sodium in its metallic state, or copper in its metallic state, or even the elemental form of sulfur is S8. All of these have an oxidation state of 0 because they're the elements existing by themselves. There's no polar bond, so we don't have to worry about that unequal electron sharing. We'll see that the oxidation state of monoatomic ions is equal to a charge. So if you have something like Na+, we're going to see that its oxidation state is +1 because it fully has lost that electron. So you can take it how many valence electrons it usually has, look at its charge, it's now +1. Cl-, oxidation state of -1. Ti3+, oxidation state of +3. Okay. Rule 3 is here because we follow it early, but we're going to use rules 4, 5, 6 to verify rule 3. But it says that the sum of oxidation states of all atoms equals the charge. So if you have something like calcium chloride, when this breaks up into ions, this is calcium 2 plus 2 Cl minus. And right off that bat, we can see that these are two monoatomic ions. So we're going to see their oxidation states are equal to their charge. So calcium 2 plus has an oxidation state of +2. Chlorine minus has an oxidation state of -1. And if we add those together, +2, which I'll do here, +2 plus 2 ions, or 2 things that have a -1 oxidation state, you get 0. Another one we'll see is NO3 minus. And we're going to loop back around to this one once we have gone through a couple more rules, because this isn't simply a monoatomic ion, it's a polyatomic. Okay. So in compounds, metals have positive oxidation states given by their column in the periodic table. And what this really means is that your alkali metals are going to have an oxidation state of +1, and your alkaline earth metals, so the second column, are going to have an oxidation state of +2. And I'll show you a table in just a second that's showing that. So that's rule 4. Rule 5 is fluorine is given a -1 oxidation state. Hydrogen is typically +1. And then our final rule, which will allow us to loop back up to number 3, is that oxygen is typically a -2. And the exception is peroxides, which we won't get too much into here. And so if we go back up here to nitrate, we see that we have nitrogen. We don't have a rule for nitrogen. And so what we're going to talk about on the next slide is that we're just going to treat that as X, and we're going to solve for it. But then we have 3 oxygens with an oxidation state, which we said is typically -2. So I'll put a -2 here, and all of this has to add to -1. So I get X minus 3 times -2 is 6. So I have X minus 6 equals -1. And so what I'll see if I add 6 to both sides is that X is equal to +5. So I'd say that this has an oxidation state of +5, this one has an oxidation state of -2, and it all adds up to the charge. And so we're going to just go and do one more example of this. So here I'm giving you the table, and then, like I said before, this was my metals adopt their a positive oxidation state. This is your alkali metals, and those include things like potassium, lithium, and sodium when they're in an ionic form. And then these are alkaline earth metals. So I'll just say alkaline earth. This is things like Mg2 plus, calcium 2 plus. Okay. Everything that's not in this table. So the first 2 columns, hydrogen, fluorine, oxygen, and the halogens. So this is things like fluorine. For all of those, we're going to see an adaptation of oxidation state to follow rule 3. to make sure that the sum of all oxidation states equals charge, which is 0 for neutral. So let's say we're looking at two different forms of carbon. So, or not two different forms of carbon, but carbon bound to two different things. We're looking at CF4 and CH4. And we're going to look at each one of these. We're going to make sure we follow our rules. So carbon doesn't have a rule. So we have, this is an unknown oxidation state. Fluorine, we look at rule 4, fluorine is -1. And so this is a neutral molecule. So whatever oxidation state oxygen adopts plus 4 times the oxidation state of fluorine of -1 has to equal 0. So we would get x minus 4 equals 0. X is equal to +4. So in this case, carbon has a +4 oxidation state. All right, so maybe we just decide carbon always has a +4. But we want to hold up. Let's check another circumstance. If we go here, carbon has an unknown oxidation state. Hydrogen, number 3, we say it's +1 in combination with all nonmetals. So now we have whatever oxidation state carbon adopts plus 4 times the oxidation state of hydrogen equals 0. Now we have x plus 4 equals 0. And in this case, now carbon has an oxidation state of -4. So these atoms that don't fall into the rules I've given above can adopt many different oxidation states based off of what environment they're in. You could do the same thing by looking at two different nitrogen compounds, NH3 and NF3. And this follows a very similar pathway where fluorine is -1, hydrogen is +1. And so in order to get neutrality, and you can think through this yourself, x plus 3 times +1 equals 0. X equals -3 here for nitrogen. And in the second case, which I'll do in black, x plus 3 times -1 equals 0. X equals +3. And so all atoms that aren't given in the table above, we have to use this approach to figure out their oxidation state. Okay? And so we'll do one more example, and then we'll work on a problem separately. So here I'm looking at CO3 2-, so carbonate. And so we're going to follow the first rules, 1 through 6. And then for an unknown, we're going to set it up like I have below, like I was doing before, where you take A is the number of that atom, and you multiply it by its oxidation state, plus B, which is the number of the second atom, times its oxidation state, has to equal the charge of the molecule. So here, carbon has an unknown oxidation state, and oxygen has that known oxidation state of -2 from rule 5. So we have 1 carbon times its oxidation state of X plus 3 oxygens times their oxidation state of -2 has to equal this charge right here, -2. So we get X minus 6 equals -2, plus 6 plus 6, X equals +4. And so we'd say that C is equal to a +4 oxidation state, oxygen is equal to -2. Okay, so that's how we would solve that problem. So with that in mind, let's look at these compounds right here. And we'll look at a couple more examples in class on Tuesday, but I want you to follow the rules we did above. And then if you have a compound that has more than one atom, you can use this formula right here. So pause the video here, assign some oxidation states, and then we'll come back around and look at them. Okay. Presumably you are back and you've had a chance to work through these, and so we're going to step through them one by one. With this first one, Cl2, this is actually chlorine in its elemental state. And so because it's in its elemental state, we'll say that its oxidation state or oxidation number equals 0 because it's in that elemental state, no unequal sharing of electrons. Sodium plus, that's a monoatomic ion. Its oxidation state is going to be +1. And now we get to some compounds. We have Kf. K is an alkali metal, so it, by its rule, is +1. Fluorine is a halogen, and we said it adopts a -1 oxidation state. You can check that it follows the rule that everything adds together to neutral. +1 plus -1 equals 0. You're good to go. CO2. C, we're not sure of, so then we go to O. We know that O is a -2. And then if we do there's a single carbon of unknown oxidation state plus 2 carbons with a -2 oxidation state equals 0. X minus 4 equals 0. X equals plus 4. So we say C is equal to plus 4. Now we'll go down to sulfur, unknown charge. We'll go over to oxygen. So oxygen, we know, has a -2 charge. So we have the single sulfur of unknown oxidation state plus the 4 oxygens that have a -2 charge on them, or a -2 oxidation state, has to equal the charge of the molecule, which is -2. So that's X minus 8 equals -2. X equals plus 6. So we'll say a 6 here. And then finally, we have a peroxide. And so that's something that I said we wouldn't deal too much with. I have it here as an example, but we won't have any of these examples in any of our exams. And we're going to follow the rule for our groups that these alkali metals like potassium have a +1 oxidation state. We see that if we gave oxygen its usual -2, we would not get charge neutrality. So we're going to have oxygen be unknown. We have 2 of these potassiums. They each have a +1. We have 2 oxygens that have an unknown oxidation state that has to equal 0. So 2 plus 2x equals 0. X is equal to -1. So in this case, this is a peroxide, and oxygen has that -1 charge. Okay? And so one thing I kind of want to illustrate to you is if I draw up sulfate, which we said its most correct Lewis structure looks like this. I put one too many electron pairs there. You can see sulfur, 0 lone pairs, and it's forming 6 bonds where all of these 6 bonds are pointing towards the oxygens. And in this case, sulfur has basically lost all 6 valence electrons it used to own. So it used to have 6, U minus 0. So that's how you get that +6 oxidation state. And then for these oxygens, overall, they averaged that -2. But we'll go in depth and we'll talk about how each one of these oxygens themselves looks. But that's how we got that sulfur was a +6 in that case. All right, so we're going to stop this video here. And then in the next one, we're going to look at doing some reactions where we'll assign oxidation states just like we did to more than one species at a time.